Hi, my name is Matthew Castronuovo, and this is my Lab 4 oscillating motion. So to introduce the lab, we are going to talk about the purpose, and that is to watch and record the position, energy, or not record, but model the energies and the forces acting on an object in oscillating motion. And some important concepts for this lab: spring force, gravitational force, which combine to cause the net force of our object in this case, and then kinetic energy and potential energy, which can be broken down into spring potential energy and gravitational potential energy. And the main results of this lab were that we observed an object that was being acted on by both the Earth and a spring and watched it oscillate and move in a seemingly random motion, but it was actually able to be predicted in a simulation. So the experiment, the system would be considered the uh, object, and the surroundings would be everything acting on the object. So the spring, the earth, the air around it. The initial conditions were that the spring was at rest but had some level of potential energy, causing it to move. And then the experiment details are that basically just this object was dropped and it was acted on by the spring and gravity. So some assumptions for our model. First of all, the only forces acting on our mass is the force of gravity and the spring force. The spring only moves in two directions, x and y. We're not saying that it comes towards or outside of the screen. If we're talking about the recording, I use the recording. Air resistance is negligible, and the data gathered from the tracker is completely accurate to the events of real life. So a possible source of error would be human error inputting data on the tracker app. So this is my model in GlowScript, and basically some important things worth noting are the first of all, if you look down in the bottom left corner, you can see the spring parameters. So L is the length that the spring is at currently, and that can be found by subtracting the position of the ball from the position of the spring. L hat is just the unit vector of that, and then S would be the magnitude of L minus the relaxed length of the spring. And then on the right hand side, we have the while loop that makes everything go. We set initials for all of our energies so that later in the code we can calculate the change in all of the energies. So these are the main results. You can see the simulation, and then the oscillation in energy, the change in energy with each of the different types of energy broken down, and then you can see the position and time graphs for the model versus the experiment. So what does this mean? Well, first of all, we can say that the energy principle is satisfied by this equation or by this experiment because no external energy or work is being done on the system to bring more energy into the system. The total amount of energy should remain the same, which it does. And we see this by the fact that the position time graph or the energy time graph waves are symmetrical about the x-axis, so they cancel each other out at every step of the way, and just shows that energy is constantly being transferred to and from potential and kinetic energy. So continuing, using the tracker data, the oscillation period is observed by measuring the time between the peaks. So for the x direction, this would be just about 1.5 seconds, and for the y direction, this would be just about 1.4 seconds. And the y oscillation is due to the spring, and the x oscillation is due to the swinging of the spring. So that's all. Thank you.